Record. All right, ladies and gentlemen. So we're going to be talking about our lesson 4.6, the tangent function and periodicity. Okay, the tangent function and periodicity. Okay, so the tangent function differs a little bit from the sine and the cosine function. If you guys remember when we talked on with 4.5, right? Our sine and our cosine functions, they had a period that was 2 pi. Okay, so if you remember, the period represents the distance of how long it takes for a full curve, like a sine curve or a cosine curve, to take place. Okay, and then it repeats every the same distance, it repeats. So for a sine and a cosine curve, you know, we have our sine curve here starts at 0, and we have this. So this is from 0 to 2 pi, right? And then it repeats the same curve every 2 pi. So this would be 4 pi, and then we continue. With a cosine curve, we start up top, and it looks like this. And this is 2 pi, this is at 0, and then it essentially repeats that curve every 2 pi, just like we were talking about, right? I didn't really want to go into notes there, guys, but it's okay. So that's for the sine and the cosine, our parent functions. The period is 2 pi, right? Our domain is all real numbers. Our range is -1 to 1. All of that changes with tangent, okay? So our goal for today's lesson is that students will be able to graph the sine and cosine. Oh, that should not say sine and cosine. My apologies. It should say graph the tangent function. I will need to edit that. Okay, students will be able to graph the tangent functions and identify the properties by completing problems as taught. That's our goal here. Okay, the tangent function. We already did the sine and the cosine. So the parent function is, this is our parent function, just tangent x. Okay. So x is our angle, right? Y is our value there. So that means that our x-axis represents our angle values, and we usually put them in radians. Okay, and then our y is just our values. Now, one thing has changed here. Actually, multiple things have changed here. I apologize. Our period now is pi, not 2 pi, pi. So it only takes a distance of pi for a full curve of the tangent curve to occur. It only takes a distance of pi. So every pi, right, every pi distance, our curve is repeating, okay? So I want you guys to quickly take a look at our trig chart. And I have you pull out your trig chart because it has tangent on it. And I want you to notice something here, okay? Notice all the places where tangent is undefined. Notice all the places where tangent is undefined. So tangent is undefined here at 90 degrees and pi over 2. And then if I continue on, tangent is undefined once again over here at 270 degrees or 3 pi over 2. Okay. So we have an undefined tangent at pi over 2 and an undefined tangent at 3 pi over 2. Because tangent is undefined in those places, that means I don't have a y value, right? Tangent of pi over 2 does not give me a value. Tangent of 3 pi over 2 does not give me a value. So when our angle hits pi over 2 or 3 pi over 2, I'm not going to have a value. And what that does is it creates asymptotes. Because we do not have a value at those angles, we end up graphically, that ends up being an asymptote. So at every increment of pi over 2 and 3 pi over 2, I have an asymptote. So what ends up happening is the distance of pi, if I were to take 3 pi over 2 and subtract pi over 2 from it, that's a distance of pi right there. If I were to take pi over 2 and subtract negative pi over 2 from it, that would be a distance of pi, right? Negative pi over 2 minus 3 pi over 2, that would be a distance of pi. So at pi over 2 and 3 pi over 2, and every increment of that, I have an asymptote, which limits my domain, okay? That limits my domain here. So that means that x cannot equal any value of pi over 2 plus whatever, however many pi's that you add to it. Because if I have an asymptote at pi over 2, I add 1 pi to it, I'm at 3 pi over 2. If I add another pi to it, I'm at 5 pi over 2. Add another pi to it, I'm at 7 pi over 2, and so on, right? It could be the same thing if I was subtracting pi over 2. Or I'm sorry, subtracting pi, right? So our domain is restricted. Our x's cannot equal pi over 2 plus however many pi's to it, or n plus or n times pi. Our range, however, notice our range here, right? Our range is actually all real numbers. So it's a little bit flipped, right? For sine and cosine, our domain was all real numbers and our range was limited between 1 and -1. However, with sine, our range is unlimited, it's all real numbers, and our domain has the restrictions of asymptotes, okay? And it looks like almost like a, what am I looking for? It looks almost like a cubic curve, right? Each time it looks like a cubic curve. You guys remember our cubic curves there, our odd functions, okay? So we're going to do what we did for our sine and our cosine values, and we're going to evaluate some of our values of tangent, okay? So let's take a look here. First things first, we have for what values of x is tangent of x equal to 0, okay? So let's see. Tangent of x equals 0, so that's y is equal to 0. We have a 0 here, where y is equal to 0. We have 1 right here. We have 1 right here. It looks like we're gonna have 1 right there. Okay, I don't know if you guys can see that. So here, 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 and here, right? Y is x. So what are those values of x there? Because we have negative pi, right? We can write down negative pi, that's okay. 0, right? That's at 0, 0 for my x. Pi, and it looks like that's going to be 2 pi at the very end there. Okay, so doing what we did before, right? It looks like every pi, right? Every pi, 0 plus pi is pi, pi plus pi is 2 pi, right? I could also do like the subtraction to see what the difference is if it wasn't as clear, right? If we had fractions and it was a little bit harder to see, we could just do that and see what the difference is there. So it looks like every pi, every distance of pi, tangent of x equals 0. So our formula for a general, right, a general pattern here, we start with our 0 plus pi times n, right? So however many pi's that we can add. So this would be 1, right? 1 pi. This would be, our n would be equal to here. My next one I could do n equals 3 and it'll be 3 pi. n equals 4, and it'll be 4 pi, and so on and so on, right? All right. So the next one is a little bit different. Okay, the next two are a little bit different here. It says, for what values of x is tangent x going to infinity? For what values of x is tangent x going to infinity? So this symbol right here, this entire thing means as tangent x goes to infinity. To infinity and beyond, right? As tangent x goes to infinity. So for what values of x does tangent x go to infinity, right? And we want to make sure we notice it's a positive infinity. Infinity. It's a positive infinity. Positivo, right? So if I take a look, that means I'm looking at the top half. I'm looking at that top half there, okay? So I can see here, well, we can go with the positive side here. I can see that my tangent x, right, is going toward infinity as it moves toward pi over 2. It's going toward infinity as it moves toward 3 pi over 2, right? It's going upward, up, and beyond, right? Okay. And then on this side, I can see that it's happening as it's going toward a negative pi over 2. On this side, I can see that it's going up toward infinity as it's going to negative 3 pi over 2, okay? So my values here, right, what values of x is tangent of x going upward, right, toward positive infinity? I would have a negative 3 pi over 2 here, a negative pi over 2. So we're talking about these asymptotes here. At pi over 2 and 3 pi over 2. Okay. So for each one of these values here, notice this doesn't say tangent x equals a certain number, right? Because these are asymptotes. It can't actually equal that number. It can't equal a number. It's undefined at those points. And so that's why we say that tangent of x is going toward infinity. It's moving in a certain direction. So as we approach each one of these of pi over 2, our function here is getting larger and larger and larger, right? So as I'm approaching pi over 2, this curve is getting higher and higher and higher. As I'm approaching 3 pi over 2, it's getting higher and higher and higher, right? So, but these are the values at which they're approaching to get to get higher. And again, the same process for writing the formula for this pattern, right? It looks like I'm going to take these two positives and subtract them and see what it is. And you all probably already know, but we're just going to show the process here. 3 pi over 2 minus pi over 2, right? The same denominator already set for me. 3 pi minus pi, 2 pi. Oh, my bad. That's 2 pi over 2. Divide that, that's going to give you pi. So the increment between them is essentially pi, right? So what does that mean? That means I'm going to take the smallest positive one, pi over 2. And that means this is moving in every pi. So every pi, right? So we're seeing that periodicity again. So pi n. All right. Next we have the next one is for what values of x is tangent x going toward negative infinity now. Okay. So this is as tangent x goes to negative infinity. So now we're moving down. We're moving down, down, down. So if you can see, we have our tangent x moving down as it approaches negative 3 pi over 2. We have our tangent x going down as it approaches negative pi over 2 there. We have our tangent x getting lower and lower and lower and lower as it approaches pi over 2. And similarly here, as it's approaching 3 pi over 2. Sounds like the same values, yeah? We have negative 3 pi over 2, negative pi over 2, pi over 2 here, and 3 pi over 2. That shouldn't shock you, right? Because these are the asymptotes. So these are the lines that we are approaching, right? But never going to actually cross. So it makes sense that they're both the same, that on one side of it, right? On one side of it, it's approaching positive infinity. And on the other side of it, it's approaching negative infinity. So our formula is essentially going to be identical. Pi over 2 plus pi over n, because it's the same values, it's the same pattern. Okay. All right, so that's our tangent function, y'all. Okay, tangent function has asymptotes. Oh, yes, it does. Okay. So, and it's a broken up function. It's not a continuous function. Or each one is an individually continuous function. Let's say that. Okay. So that brings us to this idea of periodicity. Okay. So periodicity is when you have functions that are periodic. Okay, what does that mean, Miss Kate? Periodic, okay, is a function. So a function is periodic if the values repeat in a given pattern, as we've seen with sine, cosine, and tangent. Okay, so sine, cosine, and tangent are all periodic functions. They repeat, the values repeat in a given pattern. Okay, so all of the ones we've looked at thus far, right, are periodic functions because we have our waves or our curves repeating. Okay, so what that does for us is it gives us our periodic theorem, and it allows us to graph something that might have been moved quite a bit by using this idea of periodic. So it's important to understand this idea of periodic theorem. So notice each one of these, right? Our values are repeating 0 plus pi n, pi over 2 plus pi n, pi over 2 plus pi n. So for the tangent function, our tangent function, our periodic theorem tells us that if I have tangent of theta plus pi n, then that is equivalent to just tangent of theta. Okay? If I have tangent of theta plus pi n, that's just equivalent to tangent of theta. I'm trying to find my sine and cosine one so I can show you guys real quick. Oh, where did I put my 4.5 notes? These no good. If you guys have your 4.5 notes handy, you can look at them. It's not it either. It's not it either. Guys, don't be messy like me. Don't be messy like me. No, I just didn't have. Here we go. Okay. So if you take a look, okay, if you take a look at sine and cosine, for most of sine and cosine, right, our pattern is repeating every 2 pi. Okay, our pattern is repeating every 2 pi. That's for sine, and then for cosine, when I flip it over, I have the same thing happening here. My pattern is repeating every 2 pi, right? And then this pi n, that could easily be extended to 2 pi. That's fine. So with that, right, that gives us our sine and cosine periodicity. Oh my God, I can't say the word anymore. I was doing so well with it. Periodicity. There you go. So with sine and cosine, it's theta plus 2 pi n, right? Sine of theta plus 2 pi n is equal to sine theta. And cosine of theta plus 2 pi n is equal to cosine theta, okay? So it's pretty much saying that every cycle, the values are repeating. So if you essentially simplify it down by looking at how many 2 pi's are in your angle, or how many pi's are in your angle for tangent, okay, you can actually simplify the problem for yourself and find the value itself, okay? So let's take a look at one of these examples here, okay? So we have find all values of x, for which, okay, for which sine of x is equal to 1/2 if x is in quadrant 4, okay? So first let's take a look at the fact that we want to see what values of x for which sine of x is equal to a negative 1/2, okay? A negative 1/2. So if you don't remember off the top of your head, this is why I had you guys pull your trig charts and your functions out. So if I take a look over here, right, I want to look under sine, so sine of x, right? And I'm looking for negative 1/2. Negative 1/2 here. The other way you could do it, because it's sine, you could look on your actual quadrants here, okay? And sine is negative below the x-axis, so I can simply just look right over here. I see a negative 1/2 here at 7 pi over 6, and I see a negative 1/2 here at 11 pi over 6. So I have 7 pi over 6, and I have 11 pi over 6, but they wanted it in specifically quadrant 4, right? But quadrant 4, that means that I'm looking at 11 pi over 6, not 7 pi over 6. Okay, but here's the thing. They did not tell me to only get the value that is between 0 and 2 pi. They said find all the values, right? That would end up being in quadrant 4. So what does that mean? That means I have to apply periodicity. Oh my gosh. You guys are laughing at me right now. I hope you're laughing at me because I'm laughing at myself. So we have to apply this idea of the fact that sine of theta plus 2 pi n is equivalent to the same thing. So that means that not only is sine of 11 pi over 6 equal to negative 1/2, but so is every value of 11 pi over 6 plus 2 pi n. So sine of every angle that this formula would produce would give me a negative 1/2 in quadrant 4. Okay, so that's essentially like saying, okay, here's 11 pi over 6, right? And my sine is negative 1/2 there. So this is the first one. But then this would also give me the same value. This would also give me the same value. This would also give me the same value, and so on, and so on, and so on, and so on. So it's this idea of that revolution, right? So we're literally repeating the process, and they're all ending up right here in quadrant 4. Okay. When you're ready, we can flip over to the next page, the next página. Okay. All right. Oops, sorry. Look at a blank page there, guys. Okay. So next, what we want to look at is we're going to look at the next example of, it says right tangent of, this might have happened in your notes. I know in my notes, for some reason, the formatting just like left out my pi. So right tangent of 427 pi over 6. So that should have a pi with it, okay? In terms of the periodicity theorem, periodicity theorem. I don't know. I may be saying it correctly. I may just think I'm saying it incorrectly. I have no idea. I do have an idea. I'm just being silly. Okay. So we want to write this tangent of 427 pi over 6 in terms of um, the theorem, right? So we have to remember, since we're dealing with tangent, that means the period that we're dealing with is pi, not 2 pi, right? Tangent means we're dealing with a period of pi, not 2 pi. So we need to take this value, and in order to see how many periods of pi are in this angle, I need to divide by the period, right? So I'm going to take this value here, 427 pi over 6, and I'm going to divide by the period of tangent, which is pi. So what ends up happening here? Well, that and that cancel, and I'm left with 427 over 6, which once I divide gets me 71.16 periods. Okay, 71.16 periods. So I'm going to ignore the 0.16 there. Okay, what this means is that I have 71 periods, okay, in this angle. I have 71 periods in this angle. Okay, so which means I have 71, oops, sorry, I have 71 pies. I have 71 pies in this period plus an angle, plus theta. I don't know what my theta is yet. Okay, I don't know what my theta is yet. So I need to figure that out. So what I'm going to do is I'm going to take this guy right here, my angle, 427 pi. Oh my gosh, I'm having such a struggle writing right now. I'm going to take 427 pi over 6, okay, and I'm going to subtract 71 pi from it. I'm going to subtract 71 pi from it, okay? So I need to actually figure out what 71 pi is, right, with the denominator of 6. So if I take 71 pi over 1, multiply top and bottom by 6, okay, that's going to get me whatever 71 times 6 is, y'all. And that's going to get me 426 pi over 6. Okay, so this is the equivalent of doing 427 pi over 6 minus 426 pi over 6, which equals pi over 6. So my theta, my original theta between 0 and 2 pi is pi over 6. Okay, so I can rewrite this guy. I can rewrite 427 pi over 6 as, I can rewrite it as pi over 6 plus 426 pi over 6. But I don't want to write that like that. That's nasty looking. So instead, I'm going to write it as pi over 6 plus 71 pi. Okay. So this right here is the remainder, our theta. This right here is the number of periods that we have after pi over 6. So how my final thing here is I want to rewrite tangent of 427 pi over 6 in terms of the periodicity theorem. So what that's going to look like is tangent of 427 pi over 6 is equivalent to tangent of pi over 6 plus 71 pi. Okay. There you go. There you go. Okay. So this is directly connected to what we were doing at the beginning of chapter 4 when we were looking at revolutions and we were looking at reference angles, right? And we were trying to essentially figure out how many revolutions was in that angle. Essentially, we're doing the same thing, except we're now using the periodicity of each angle. So if this was a sine or a cosine function, I would be dividing by a period of 2 pi, right? Not just pi. Because it was tangent, we were doing pi. But if it was sine or cosine, we would be looking for how many periods of 2 pi are in this angle, right? So it would be significantly less because it's 2 pi. Now, our activity and homework for today, funnily enough, does not actually involve graphing tangent quite yet. It is somewhat linked to this idea of periodicity, but our classwork and homework for today is mainly focused on solving, okay, finding general solutions of trigonometric equations. Okay, now a general solution means we are going to be writing it in a form. Our answers should be in some form of formula where the pattern is continuing, okay? So I want you guys to keep your note sheet handy because I'm going to do a few more examples on this note sheet here. But I want to do the first example right here on your 4.6a classwork, okay? So general solutions of trigonometric equations, okay? So we want to find the general solutions for each equation. There might be more than one general solution, especially if I have not indicated a quadrant. Just throwing that out there, okay? So let's take a look. How do we solve a trigonometric equation? Well, you treat the entirety of sine x or cosine x or tangent x. You treat this entirety as your variable. So the goal is to get this guy by itself, right? And that's just going to take some basic algebra. So I'm going to subtract a 1 from both sides. So I'll get 2 sine of x is equal to -1. And then the 2 is outside, so I'm going to divide by 2 here, outside of the sign, right? It's not inside. So I'm going to divide by 2 here, and I will get sine x is equal to -1/2. Okay? Sine x is equal to -1/2. So this is now where we look at, okay, where is sine of x equal to a -1/2, right? What values of x give me sine of x equals to -1/2, okay? So I can look on a graph for that. I can easily take a look and see, okay, -1/2 is right here. So I can look to see where my sine of x gives me a -1/2. And instead of predicting it, right, I can also bust out my unit circle / trig chart, right? And I can look to see where sine of my sine theta, right? In this case, x is theta. right? So what theta is sine and negative 1/2 for? Okay, so we have 7 pi over 6, and we have 11 pi over 6. Okay, so this would mean that x is equal to 7 pi over 6 and 11 pi over 6, because those are the x values where when I take sine of that angle, I get negative 1/2. But this is only between 0 and 2 pi, right? They want general solutions. Okay, so we need to write them in their forms, in their periodicity forms. So it's not just x is equal to 7 pi over 6 and 11 pi over 6. We have x is equal to 7 pi over 6 plus 2 pi n, okay? As well as x is equal to 11 pi over 6 plus 2 pi n. Why 2 pi? Because we're talking about sine. And the pattern repeats every 2 pi for sine. Okay. Does that make sense? Hopefully. Okay. Let's do another example, and I'm going to actually, you guys are going to be doing these 5 examples, but in your notes as a continuation, I want to do a few more examples so we feel like we've seen a few more examples here. Okay. So the next example I want to do is, let me make sure you guys can see what I'm writing here. Yeah, okay. So the next example I want to do is 4 cosine squared x minus 1 equals 0. 4 cosine squared x minus 1 equals 0. So here, again, we're going to be solving, right? And we're trying to get cosine x by itself. But this is being squared, so there's definitely going to be some square rooting happening there, right? So we need to make sure that we are paying attention to that right there. So first thing first, we're going to try to get cosine squared x by itself. So we're going to add 1 to both sides, and we'll get 4 times cosine squared x is equal to positive 1. Okay. Then I'm going to divide by 4 on both sides, and I will get that cosine squared x is equal to 1/4. Okay. I'm not looking for cosine squared x. I'm looking for cosine x. So we will square root both sides. Okay, that will cancel that, and I'm left with cosine x, as I should be. And here you really have to remember that when you square root something, right, you get 2 values. So you're going to get plus or minus. Square root of 1 is 1. Square root of 4 is 2. So I get plus or minus 1/2, right? So I'm looking really here, I'm looking at 2 values. I'm looking at cosine x is equal to a positive 1/2, and I'm looking at cosine x is equal to a negative 1/2. So really, I'm looking at 2 values. So I'm actually all over my unit circle here, right? I'm going to be all over my unit circle here because I'm not just looking for my negative 1/2 values, right? I'm not just looking for my negative 1/2 values. I'm also looking for my positive 1/2 values, right? The positives here and here and here and here, or they could be up here. So what do I do then? I take a look and I see, okay, for what values of x, look at the positive 1/2 first. What values of x is cosine x equal to a positive 1/2? Okay, positive 1/2 here I have at pi over 3. Okay, so it's going to be pi over 3, comma, and then I'll also have another positive 1/2 right down here at 5 pi over 3. Okay, so I'm talking about cosine, right? So periodicity tells me that I'm going to be, my x's are not just these guys here, but they are going to be pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n, as well as Now I look at my negative 1/2. Okay. Well, cosine here is negative 1/2 at 2 pi over 3 and negative 1/2 at 4 pi over 3. So I have 2 pi over 3 and 4 pi over 3. And periodicity tells me I have 2 pi over 3 plus 2 pi n and 4 pi over 3 plus 2 pi n. So those are my x values here. Now, if my directions had said 0 to 2 pi, only between 0 to 2 pi, or in a specific quadrant, I would just give one answer, right? Or I would have just one of these guys based on the quadrant. But because I don't have a specified quadrant, I'm looking at all of these, right? Okay, let's do another example here. Okay, so we have 2 sine squared x plus 3 sine x plus 1 is equal to 0. Okay, notice each one of these starts off at as equal to 0, which we want it to be since we're solving, right? This should look familiar, like a familiar format. Does it look like a familiar format to you guys as far as like an equation goes? Does it look like anything you've seen before? I know it's been a long set of notes, guys, but I want to give you a variation of equations, right? Yeah, Wally. Yes, this looks a lot like a quadratic. You have your x squared, your basic x, and your oh my gosh, I'm blanking on the word, constant. Thank you. So I have think of this as 2x squared plus 3x plus 1, right? So if we were to solve this as a quadratic, I would be looking at it like this. 2x squared plus 3x plus 1, right? Where x is sine of x, right? Where x is sine of x in this situation. So we kind of want to treat it like a quadratic as we're solving it, right? We want to treat it like a quadratic here. And we're going to factor it like a quadratic. Do you guys remember how to factor quadratics? Okay. So if I were to try to factor this, right, we have the x method. That's one. Guess and check is another great method. Okay. But one thing to consider is that our values here are going to be 1 and 1. This is actually a very simple quadratic. Okay. We're going to end up having our two values here. Okay. Now, the two factors that multiply to 1, are pretty much 1 and 1. And our two factors of our coefficient here, 2 and 1, right? 2 times 1. So one of these is going to be 2 times sine x, and the other one is just going to be 1 times sine x, which honestly, we can just ignore that 1 altogether there. Everything is positive, so it's just going to be plus and plus, okay? But I mean, if you really wanted to, you could look at this with the x method, right? Remember that x method, you have a times c and then b down here. Our a, 2 times 1, right? That's going to be our 2 here. And then our b is 3. So what factors of 2 multiply to get 2, but add to get 3? Well, that's just going to be 2 and 1, right? And so you would kind of do like the borrow method here, and then the borrow and factor. So you would do 2x plus 2 from here, and 2x plus 1 from here. But since you borrowed an extra 2, you're going to factor it out from the one that you can factor it out from. I know this is really fast. That's because this is very big review. And that drops, and so you're left with x plus 1 and then 2x plus 1. 2x plus 1, that's your 2 sine x plus 1. X plus 1, that's your sine x plus 1. Okay? But the purpose here is once you factored that, you split each one and you solve individually, right? That's the factor theorem there. Okay? So you get over here 2 sine x is equal to -1. So then sine of x is equal to -1/2. And then over here, you'll get sine x is equal to a -1. And so now you're looking at the different variations of this solution. Okay. So you'll essentially have sine of x is equal to a -1/2. We kind of already did that on our example up here, right? So we had our sine of x is equal to -1/2 at 7 pi over 6 and 11 pi over 6. Okay, so we have 7 pi over 6 and 11 pi over 6, right? So this is going to be, this we're talking about sine. So that's going to be 2 pi n. So 11 pi over 6 plus 2 pi n. And then sine is -1 only in one place. Sine is -1 only at 3 pi over 2. So that means this is going to be x is equal to 3 pi over 2 plus 2 pi n. Okay. We have one more example and then I'm going to be done, guys. Okay. I want to give you this other example here. What if you had this? What if you had, here, let me do this for you guys. What if you had tangent of 3x is equal to 1? What if you had tangent of 3x is equal to 1? What if the change was within the angle, right? What if the change was within the angle? Well, in this situation, you would, if I had anything else outside here, if I had like another number outside of tangent, or if I was adding something outside of the 3x and whatnot, I would still get tangent 3x by itself. So once you get this, the tangent of your angle by itself, then you go to your chart and you look at, okay, when is tangent of an angle equal to 1? When is tangent of an angle equal to 1? Okay, well, there's a few places that happens. The first place is at pi over 4. Okay, and I'm literally looking at my trig chart for this one because tangent is not on my unit circle. So I'm looking at my trig chart here. So tangent is 1 at pi over 4. And it does 1 again at 5 pi over 4. Okay, so it does 1 again at 5 pi over 4. So I have pi over 4 and I have 5 pi over 4. Okay, so how does this help me? Okay, you have to be careful here because this does not mean that x is equal to 5 pi over 4 and 5 pi over 4. On the contrary, it means 3x is equal to pi over 4 plus, in this case, again, you have to be careful because the periodicity of tangent is pi n, right? So I have 3x is equal to pi over 4 plus pi n. I also have 5 pi over, I'm sorry, I wrote that wrong. I also have 3x is equal to 5 pi over 4 plus pi over n, okay? So I have to solve, right? I have to solve for x. I don't want 3x, I want x. So I'm going to divide everything by 3. Okay? Same thing here. Divide everything by 3. Okay, so what happens? That cancels. I get x is equal to pi over 4 divided by 3 becomes pi over 12 plus pi over 3n. Right? And then over here, again, the 3's cancel here. Same thing, 5 pi over 4 divided by 3. I get 5 pi over 12 plus pi over 3n. Okay, and those, so when you have something like anything happening with your angle, you pull the values from the unit circle, and then that angle equals that periodicity statement, that general statement, and then you solve for that x. Okay. Okay. So you guys have 20 minutes to work on these 5 problems. Okay, 20 minutes to work on these 5 problems. I think I did an example of each one. Remember that I am looking for general solutions, okay? Not just a one single solution. So you need to be giving me that periodicity. If I give you a quadrant, then you would only have one formula for me. If I don't give you a quadrant, then you got to give me every possible one like I did for you guys in the examples, right? Any questions? So this is your classwork, and your homework is a bit of the same, okay? So your homework, you have 10 problems, and again, you're solving, okay? Find all solutions to each equation in radians. That's what we want, all right? Okay, I'm gonna let you guys work. I am here. If you have questions, please make sure that you get them answered before class is over. Remember that I also have tutoring on Thursdays from 2:15 to 3:15, okay? And again, I'm here if you have questions.